Example 9 says plus or minus students square root of 81 times n squared. So a plus or the minus in the front, it's the same thing as saying plus or minus 1 times square root of 81 times square root of n squared. Well, square root of 81 students is going to be 9, so that's going to be times 9. And right now we're going to say square root of n squared. Well, square root of n squared, that's going to be n times n. Well, that's 2n's, and because it's square root, we can take it out. So currently we are going to say this is going to be positive or negative 9n. Okay, so positive or negative 9n. Now similarly to square root of x plus 1 to the 4th. Well, how do you know what the answer is? Well, x plus 1 to the 4th means there are 4 of these, right? X plus 1, there's x plus 1, and x plus 1, like that. That's what it means to have a power of 4. Well, we said every time you see a square root, we need 2, right? Just kind of take it out of the simple radical. So that means it's n plus, why do I keep saying n? X plus 1. And then we have a second set there because we have 2. So now we have to multiply them back as x plus 1 quantity square, just like that, okay? Well, we have cube root. So cube root, we know that the cube root of 8 is 2 because 2 times 2 times 2 is 8. So that's going to say, okay, well, break it down, index of 3, 8, and then times cube root of n squared, just like that. Well, this comes out to be 2. Well, n squared, there's only 2 of them, so that doesn't really help us simplify out of the square root. So we kind of keep it just like that, okay? Well, so simplifying radicals has an issue, especially if we are going to run into variables, okay? So let's talk about, let's see what we just got done. We just got done with 11, so I'm looking for 12. So kind of talk about something like 12. Cube root, we know we can have negatives under this radical symbol. So cube root of 125 is going to be negative 125 is negative 5 times negative 5 times negative 5, just like that. And a to the 9th power, think of it as 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 of those, right? Well, we know because it's a index of 3, every set of 3, we can take 1 out. So, well, but if we keep writing these a's 9 times, what if we have a to the 91th power or a to 500, and 13th power? We're not going to sit here and write it out like this every time. So if we know the exponent is 9, you can do a to the 9th and then divide it by the index like that. That will give us a to the 3rd. And sometimes you're going to have leftovers. Not everything's going to be divisible perfectly by 3 or by 5 or whatever the index is. So that maintains inside. So in this case, we have a to the 3rd. Okay. So cube root, we definitely could have negative numbers. But what happens when we have a square root, like example 13? Could square root have negative numbers on the inside? For example, like this. We can't, right? Because that's going to be imaginary numbers. So that's not going to be possible. So when we have a square root, we have to know that only, right, positive numbers can go inside. In this case, we could have a positive x times a positive x to make a square root. And then our answer has to be x. So whatever comes out has to be positive. But think about this, guys. On the inside, we have a square, but isn't that means this also gives us a power of x to the 2nd power? But if we stick this all under a square root, isn't this right here an imaginary question mark? It is, right? But remember, we can't have negative numbers under the radical. So that's why when we have variables, it's a little bit now harder to understand because of this, okay? Because we can never, students, have negative numbers on the inside of your radical. We go and put absolute value around our final answer to make sure that whatever comes out will always be positive, okay? So that is going to bring us to the rules here. We want the positive answer. And since we don't know whether a variable is positive or negative, we use absolute value symbols. So when do we use it? When our index is even, such as square root, fourth index, sixth index, right? And when your variable, which is on the inside, the radicand on the inside has an even exponent, and your final answer ends up with an odd exponent. Okay, so let's look at a couple of cases. Example 14. Your index, students, is 4. So that is an even index. So that currently qualifies for, hey, let's see if it follows the next two check marks. Is the power on the inside even? Yes, it is. So even index, checked. Even power inside, checked. And then is your final answer odd power on the inside, on the outside. Okay, and let's simplify it. Well, we have m to the fourth and fourth index. That's m to the fourth is definitely m times m times m times m. That's how we get m to the fourth. Since it's a fourth index, our final answer is going to be, see, I must love the letter m to n today because I keep using it. So we know that the final simplified version is m, but m to the 1 is an odd index. So yes, this, guys, needs an absolute value. So now we go put an absolute value around our final answer if all of these conditions are met. So let's check our conditions again, okay? Make sure we know that if we have an even index, then we have to pay attention. Then if our variable on the inside has an even exponent, then ooh, yes, we definitely need to pay attention. Then if our answer has an odd exponent, then absolute value is needed. Let's remember those, okay? 15, fourth root, guys, of a to the fourth and n to the fourth. Oh my. Even index, okay, checked. Both a and n has what? Even powers, right? So both of them have even power, checked and checked. So now we need to simplify to see if our answer will end up with an odd exponent. So a to the fourth with the fourth index. So we have an a as an answer. N to the eighth, guys, that means there are 8 n's, okay? With a index of 4, that means we can take out n square. Well, n square, that final answer is not an odd index, but a is in 1 power, so a is an even index. I'm sorry, a is an odd index, so we need an absolute value around a because a has an odd power. My apology, not odd index, odd power. But n has, final answer of n has an even power, so we do not need to have an absolute value around the n, but just around the a. And you don't have to write this power of 1 right there, so you can just write absolute value a like that. So absolute value a times n squared, and box that up. So we have 4 examples left. Okay, let's check to see which one has even indexes, and those are the only ones that we have to worry about putting absolute values on the variables. Okay, example 16, index is 5. We don't have to worry about absolute values. Example 17, square root. Ooh, so let's put a dot on there to make sure we know that we might need an absolute value. Example 18, index of 3, not needed. Example 19, ooh, index of 6. So we are gonna make sure we double check on 17 and 19. 16 and 19, we're just gonna do it as normal. Okay, ready? Fifth index, guys, of 32 times x to the 5th times y to the 10th. So fifth index of 32, if you don't know that's a perfect fifth root, then we can start with 2 times 16. 16 is 2 times 8. 8 is going to be 2 times 4, and 4 is going to be 2 times 2. So as you can see, 32 is a perfect fifth index, okay? So that allows us to say, okay, well, 2 goes out, x to the 5th. Remember, if the index is 5, you take the power of 5 divided by 5, so we just have an x left. We have a power of 10 here on the y, so if we go y, 10 divided by index of 5, so we're going to have a y to the 2nd. So final answer box it up. We don't need to worry about absolute value because it's an odd index. We talked about 17 having an even index, so we do have to make sure we double check it at the end. So we have a negative in the front, so pretend it's a negative 1 times square root of 121 times square root of a to the 6th. Yes, you can break it up just like this if you want to. All right, so square root of 121, that's going to be 11, okay? A to the 6th index is 2, guys, so if you do 6 divided by 2, that's going to be 3. So now we have a to the 3rd. B squared, that's going to be 2 divided by 2 is 1. Okay, so remember, this is an even index since it's a square root, right? So final answer is going to need an absolute value around the a cubed and the b because both of those powers are now odd. So remember, if you go from even index to even powers on the outside and it's ending up with an odd powers on the outside, then we need absolute values. Okay, so negative 1 times 11 is negative 11. Absolute value, a to the 3rd, b, and box it up. So this is an absolute value, so make sure we make it known. Okay, box that up. All right, we have 2 more. Cube root of 40. 40 is going to be 2 times 20. 20 is 2 times 10. 10 is 2 times 5. So it looks like we have 3 2s and a 5. Okay, so definitely take out a 2. A 5 is going to stay on the inside since it does not have a set of 3. A to the 3rd with the 3rd index, that's going to give us a to the 1st power. We do not need to worry about absolute value since our index is odd. Y to the 5th, guys. Y to the 5th divided by our index of 3. So that means I'm going to have 1 full y. And then there are 2 y's left. Since I have 2 y's left, it's going to stay on the inside just like that. Okay, so on the inside, I will have y squared. On the outside, I will have 1y. So it's going to look more like this. 2 times a times y left over cube root of 5y squared. Box that up since we do not need to worry about absolute value. 19, we do have to worry about absolute value since our index is even. So x to the 18th power, we are not going to sit here and write it out 18 times, but 18 divided by 6 is going to be x to the 3rd. Ooh, odd, yes. Y to the 12th, 12 divided by index of 6 is y squared. Now out of those 2 answers here, not 2, I'm sorry, 2 variables, this is the only one that's going to need an absolute value because that's the only one that has an odd power for an answer. Box it up.